Have you ever considered what happens when a critical part of a vast digital system unexpectedly fails? Imagine the disruption if a major online service or essential infrastructure were to suddenly go offline. Redundancy for fault tolerance is the strategic practice of duplicating critical components within a system to ensure continuous operation and minimize service interruption even when individual parts experience failure. It is about building systems that can withstand unexpected disruptions without completely shutting down. The core mechanism behind redundancy acknowledges that hardware components can malfunction, software can crash, and network connections can drop. Instead of hoping failures do not occur, redundancy proactively prepares for them. It is not just about having a backup. It is about having a ready-to-use duplicate that can instantly take over. We implement various types of redundancy. Hardware redundancy includes things like multiple power supplies, redundant network interface cards, or disk arrays for data protection. Software redundancy involves running multiple instances of the same application or replicating databases across several servers. Network redundancy means establishing multiple paths for data to travel or having duplicate switches and routers. Furthermore, geographic redundancy distributes system components across different data centers or cloud regions to protect against large-scale outages or natural disasters. The concept of N+1 redundancy describes having one extra component beyond the minimum needed for normal operation, providing a single spare for immediate failover. To put this into practice, systems often use load balancers to distribute incoming traffic across multiple application instances, so if one instance fails, the others continue processing requests. Databases frequently employ automatic failover mechanisms, where a primary database replicates its data to one or more replica databases. If the primary goes down, a replica is promoted to primary, often without manual intervention. There are also different states for redundant components, such as a hot standby, where the backup is fully running and synchronized, or a cold standby where it needs to be started and configured. Advanced monitoring systems are crucial to detect component failures quickly and trigger these failover processes automatically, ensuring a seamless transition. This sophisticated approach introduces concepts like active-active versus active-passive configurations. In an active-active setup, all redundant components are simultaneously processing requests, providing both fault tolerance and increased capacity. An active-passive setup, conversely, has a primary component serving requests while the secondary waits in a standby mode. A well-designed redundant system also supports graceful degradation, meaning if a part fails, the system might operate with reduced functionality or capacity rather than crashing entirely. Redundancy is a cornerstone principle of high availability and ensures that systems remain as operational and data stays accessible even in the face of inevitable component failures. Ultimately, embracing redundancy in system design means building an inherent resilience that prepares for the unexpected. It ensures uninterrupted service, safeguards valuable data, and fosters profound trust with users who depend on reliable access. By strategically duplicating critical elements, organizations can maintain operational continuity and deliver robust performance under diverse conditions.
If this helps you code smarter, like, subscribe, and stay tuned for more.